Hey everybody, Dr. A here, and in this video we're going to be providing some background information and exploring an example of how to deal with moving loads on beams. So similar to what we talked about with trusses, we are going to analyze moving loads on beams using influence lines. Now remember, what is an influence line? Well, an influence line shows the variation of some kind of load effect as a moving load moves across the system. And specifically, it's a dimensionless unit moving load moving across the system. So if you're a little rusty on that, go back and check out one of my previous videos where we dive into kind of the generic background information on influence lines, okay? Now, when we talk about beams, the load effects of interest are typically going to be reactions, internal shear force, and internal bending moment. And so what you want to do is ask yourself the following questions as it pertains to moving loads on beams. First question you want to ask yourself is, how does the support reaction change as a unit load moves across the beam, okay? And specifically, this is a dimensionless unit load, which means it does not have actual defined units. It's just going to be a magnitude of 1. The next question you might want to ask yourself is, how does the internal shear force at a specific point change as a dimensionless unit load moves across the beam? And then similarly, the third question you want to ask yourself is, how does the internal bending moment at a specific point change as a unit load moves across the beam? Okay, so again, if you're a little rusty on moving loads and influence lines, go a few videos back and check out that background information and see the application to trusses that we've already covered, okay? So how do we sketch influence lines? Well, we can do it a couple of ways. One way we can do it is what's called the brute force method. That's where we use method of sections over and over again to calculate a load effect of interest. And then we do that based on the moving load being at several specific locations all along your system. We use the brute force method when we sketched influence lines for trusses, okay? Now, what we also can do, and this next bullet point here is more useful for beams, we can derive what are called influence functions by placing that dimensionless unit load at an arbitrary location X, and then using equilibrium procedures to derive an influence function. This methodology is a lot more user-friendly when we're sketching influence lines for beams. It's not as user-friendly as trusses, which is why we did not do it for trusses. We used the brute force method for trusses, okay? Now, a couple of things that are specific to beams. There will be discontinuities in shear and moment influence lines when we are dealing with beams. And we're going to explore that actually in a later couple of videos on this topic, okay? So let's jump into a quick example of developing an influence function, okay? Now remember, two methods to sketch influence lines. There's the brute force method, which we covered in a previous video, and we applied it to trusses. Now there's this method we're talking about in this video, the influence function method, okay? So in the given information, we're being asked to derive the influence function for the vertical reaction at A, okay? And here we have a simply supported beam. We have a roller at A, a pin at B. The beam has some length L, and then we have this dimensionless unit load with a magnitude of 1 that could move along this beam, okay? So, for example, that unit load would start here, and then it's going to move to a new location. It's going to move to a new location. It's going to keep moving along this beam until it's off of the beam, okay? And instead, the difference, though, is instead of using the brute force method like we did in some previous videos where we use method of sections over and over again to recalculate a y for these different locations, we're going to derive a function that captures this behavior all at once, okay? So let's go ahead and do that. I'm going to start by saying solution, and then what I'm going to do is I'm going to go ahead and redraw this beam. And I'm going to go ahead and draw here, you know, kind of like a free body diagram of the beam. So I've got an AY, and of course, I do have a BY and a BX, but I'm not interested in BY and BX because the problem is only looking for the vertical reaction influence line or influence function for A. So that's what I'm really interested in is AY. Now I'm going to go ahead and I'm going to place this unit load 1 on the beam. Now, where is 1 located? Where is this unit load located? Is it located at x equals 0? Is it located at x equals L over 2? No, it's located at a general variable distance of x, okay? So I'm going to say this location is x. All right, and this is the beauty and the power of an influence function. It's not going to be as tedious as the brute force method. So watch what I'm going to do now, okay? I'm going to write AY as a function of x. So I'm going to make a note here. I'm going to say write AY as a function of load location x, okay? And so how am I going to do that? Well, I'm going to say sum of the moments about point B equals 0. And I'm going to use this equilibrium equation to get this function for AY. So I'm going to have minus AY times what? Times L. Remember, this entire length is a length of L. In fact, let's go ahead and just sketch that on there real quick. So that's L, okay? So I'm going to have AY times L minus, right? And then I'm going to have plus that unit load 1 times what? What is this moment arm from the unit load to point B? Well, that's L minus X, okay? So I'm going to say L minus X here, and then that's it. That equals 0. So here I can do some rearranging, and I can get this influence function. I can say AY is equal to what? Well, that's just going to be L minus X divided by L, okay? So all I did was I rearranged and I solved for AY. Now, you can write this a little differently if you want. You can write this in a more familiar form as a linear equation. That would just be minus X over L and then plus 1, right? Because if I split this L up into a common denominator of this L and this X in the numerator, I get this form of the function. And this is it. This is my answer. Well, either one of these. You can write it as either one of these forms, and that's your answer. Now, notice this is a linear function, right? This is a linear function with a negative slope and a y-intercept of 1. So if I wanted to sketch this, what would that look like? Well, I'm going to go ahead and sketch this out so we have an idea of what this could look like. So here's AY, here's X, okay? And I'm going to go ahead and rewrite my function here. We said AY was negative X over L plus 1, okay? So the slope of this line is negative 1 over L, and the y-intercept is 1, okay? And of course, the independent variable is X, the dependent variable is AY, okay? And so if I were to sketch this out, what shape is this going to look like? Well, that's just a line. It's going to look something like this, okay? And so this value right here, that's 1. And then when x equals L, what is the value? Well, if you substitute in x equals L here, you get negative 1 plus 1, so you get 0 here. And this is your influence line. Now, this is a very similar shape as the influence line we developed in a previous example using the brute force method. So this is a lot more efficient though. Notice that we did not have to do equilibrium processes over and over again, okay? In this case, we wouldn't have really had to do method of sections because we're just getting AY. We would have just had to do AY calculations over and over again. But, you know, when we looked into this topic for a truss, we had to do method of sections over and over again because the effect we were interested in was a member force, okay? So again, we're kind of taking this concept and we're applying it to beams now. So again, if you are a little rusty on influence lines or you want to see them applied to trusses, I've got some other videos for that you can check out. Hopefully you found this helpful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.